Hey guys, you know who I am, and you know that we've been talking about pressure and volume before, and I've told you that they have an effect on the enthalpy. So that can get really confusing. So let's standardize that with the standard enthalpy of formation. So it is the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements at their standard states at 25 degrees Celsius. So we're equalizing everything. We're saying a constant pressure, constant volume, constant temperature. We're making everything constant. The standard states are going to have to follow some kind of definition, though. For gases, the pressure is going to be 1 atmosphere. In solution, the concentration is 1 molar. If it's a pure substance in a condensed state, so that means it's a liquid or a solid. Because if it wasn't a liquid or solid, it'd be a gas. Then it's going to be a liquid or solid, and it needs to be under one conditions at 1 atmosphere and 25 degrees Celsius. These values are really constant and actually are very constant, and they're found for reference in the back of your textbook in Appendix 4. And if you see them on the test, and you will see them, they'll just be given to you. No need to memorize all these enthalpies. But the degree symbol up here means that it's the standard enthalpy. So this is, when I say standard, I'm talking about the standard pressure and volume. So that's what the degree symbol means. And it will be the heat of formation of products minus the sum of the heat of formation of reactants. The sum of the products minus the sum of the reactants. And when we do these calculations, we'll still follow the Hess's law type of calculations, but we need to remember some guidelines. We need to multiply the standard enthalpies of formation by their integers required by the balanced equation. So if there's 6 moles of some substance, we need to multiply the standard enthalpy by 6. And the elements and diatomic compounds like hydrogen and oxygen and nitrogen are not included in the standard enthalpy reactions. So they're actually just going to be 0. So let me show you an example. If I consider this reaction, and notice that they're all gases. I have ClF3 plus ammonia yields nitrogen plus fluoric acid and chlorine gas, and that gives my delta H is a lot of energy, 1,196 kilojoules per mole. So if I'm calculating the delta H for ClF3, I gave you the ammonia, the delta H, the standard enthalpy formations of ammonia and hydrofluoric acid. So let's calculate them out. I'm going to take the products and then subtract them by the reactants. So here's the products, and I'm going to subtract them by the reactants. Ooh, that's a terrible line. So when I do that, I notice that the products has 2 diatomic compounds in it. The chlorine gas and the nitrogen gas are going to be 0. And then I take 6 times the standard enthalpy formation of hydrofluoric acid, and then I subtract it by 2 times the standard enthalpy formation of ClF3. That's what I want to know. And then I am adding it to 2 times the standard enthalpy formation of ammonia. That's a mouthful. And then I know that the total is going to be 1196 kilojoules. So when I calculate that out and do my algebra, I find out that this is the sum of this term, or this is this term, and then subtracted by all of this term. I'm going to switch the signs around and move my constants to the other side, and then I will divide by 2. So my delta H for ClF3 is going to be negative 1,365 kilojoules. So this is it, the end of the chapter 6. So I'm going to check for your understanding. I'm going to turn off the camera and give you 2 sample multiple choice questions. So draw diagrams to help you solve these questions and come to me with the answers.